Hello, my name is Michele Weiland. I'm a Senior Research Fellow at EPCC at the University of Edinburgh, and today I'll be talking about EPCC's catalyst system and our experience with it over the past couple of years. For those of you who don't know EPCC, we are the supercomputing centre at the University of Edinburgh. We're 30 years old in 2020 and we have around 110 staff. We are the UK's HPC national service provider and do a wide range of work from HPC to data analytics. We run two very successful MSc programs around HPC and HPC data science. I also have a growing PhD program. The Catalyst UK program that we're part of is a collaboration between Hewlett Packard Enterprise, ARM and SUSE, and three UK universities, the University of Edinburgh, the University of Bristol, and the University of Leicester. And the idea was to deploy ARM-based HPC systems across these three academic sites to further the ARM ecosystems among researchers and commercial users. The installation took place just under 2 years ago, and the system will be operational for at least another year from now. The systems themselves are HPE Apollo 70s, and the clusters at each university, at least from a hardware perspective, are largely identical. They're designed, built, and supported by HPE. The systems are 64 nodes each, 4,000 cores per cluster, sitting in 2 racks, and each node is dual socket with Marvell ThunderX2 CPUs. So there are 32 cores per CPU, 64 cores in total per node. Each node has 128 gigabytes of DDR4 memory, and we use Mellanox EDR InfiniBand as the interconnect. EPCC's system is called Fulham. It was delivered and installed at the end of November 2018, so as I said, just under 2 years ago. It was named after Elizabeth Fulham, 18th century Scottish chemist, the first person to describe the process of catalysis. And our particular objectives for the systems are to port applications to ARM, to try out different system software options, to measure the performance, and as we meet them, report bugs and collaborate on resolving them. So the original system setup as it was delivered was SUSE Linux Enterprise version 12 for the operating system. We had a PBS Pro resource manager as a batch scheduler, and a small NFS storage, a mix of SSD and spinning disk. And the system worked very, very well out the box. After it was delivered at the end of November, it was installed, and less than a week after it was installed, we used it to run a training course with 30 attendees. So we're very impressed with how easy it was to get the system set up and running with active users. We're very quickly also able to produce first results on the system. Within a few weeks of the system being installed, we had managed to port a whole host of codes and get some results on it. In fact, and submitted a paper which was published at PASC 2019, which took place in June, so only a few months after the system was installed. And this paper focused in particular on comparing the performance of a range of applications up to 32 nodes. The main systems we compared against were Intel systems. So this is typical of the type of results in this paper. This is a GROMACS benchmark of 1400 K atoms. And here we're comparing Fulham, which is the HPE Apollo 70, the blue line, against a Cray XC30, an SGI XA with Intel Broadwell processors and a Skylake processor system. As you can see, the performance of Fulham, the blue line, is pretty good. It's not quite as fast as the green or the red lines, but it scales very well. So this paper that we published at PASC has a whole host of performance results like this. But there were some drawbacks to the original setup. What we wanted was Slurm rather than PBS, but this was not supported by SLES 12 on ARM. We also wanted a fast parallel file system, preferably Lustre. Again, this was not supported by SLES 12 on ARM. And the other thing we wanted to do is for the CPU to be able to do frequency scaling and turbo states on SLES 12, the CPU was pegged at a particular frequency, and we wanted it to be able to scale up and down. Again, not supported. And you should be able to see a pattern there. So SLES 12 as an operating system did not support really the setup that we wanted. So the only choice we had was to upgrade to SLES 15, which in theory supports all of the above. So one of the first things we did after we upgraded the system to SLES 15 is to play around with frequency scaling. And here's an example of the CASTEP computational chemistry running a small benchmark of single node and looking at various CPU frequencies. What we're doing here is pegging the frequency of the CPU by hand, so setting it using the user space governor, and looking at how the performance changes as we increase the CPU frequency. The blue dots here are 64 MPI processors, and the orange dots are 32 MPI processors with 2 OpenMP threads. And as you can see, the performance, which here is the runtime that is normalized to the lowest frequency, the performance improves as we increase the CPU frequency, as we would expect. The faster the CPU runs, the more performance code gains. However, when we get to a higher regime of the CPU frequency from 1.9 gigahertz onwards, the performance stagnates and is pretty flat. There's hardly any performance to be gained from going above 1.9 gigahertz for the CASTEP code in this case. Similarly, we're then running the LAMPS molecular dynamics application with again, fairly small benchmark called rhodopsin, again running on a single node, this time using 64 cores and 32 cores. Both times this is MPI only, but the 32 core run only uses every second core. As you can see again, the performance improves as you increase the CPU frequency. In this case here, the y-axis is the normalized time steps per second. So the performance improves as you increase the frequency, but it plateaus again. This time it benefits slightly longer than CASTEP, but from 2 gigahertz onwards, the performance is flat. This is an example of stream. So a benchmark that measures memory bandwidth, so completely dominated by memory bandwidth. This is not a particularly optimized run. That's not the point of this graph, but it shows how if you increase the CPU frequency, even with a code that is memory bound, the performance improves. But again, you get this plateau at about 2 gigahertz. We see here a performance of about 215 gigabytes per second at the top range, and about 125 gigabytes per second at the lowest range of frequency. So together with ARM, we then developed a script called EFI TX2 Manager. Because we now had the latest version of the operating system, we also were able to install the latest versions of BMC and UEFI firmware. And this gave us the ability of EFI variables that we can use to change hardware configuration at boot time. So this was previously only possible via low-level firmware, but now we could do this from user space. And we can use this script to change the node configuration and reboot the nodes from user space as we want to. So we can change the number of cores that are used per CPU, what turbo modes are used, what memory subsystem speed is used, how many threads per cores are used, and so on. And another tool that we've been using is called TX2Mon. This can be used to monitor the core frequency, the temperatures and the power used by each core. This can also do things such as flagging external throttling events. And this has been already extremely useful in showing us when nodes maybe don't run at the frequency or at the temperature that we expect them to run. So with these two tools together, we've been able to do some investigation into the performance of codes and the power usage. But before we get to that, just have a look at one of the options that we can set with this script to change the EFI variables. And one of them is called memturbo. Memturbo is the setting that changes the the frequency of the memory subsystem. And you can turn it on or off. If you have memturbo on, this means that the memory subsystem frequency is pegged at 2.3 gigahertz and it doesn't change, regardless of what the CPU frequency is. But as a side effect of having the memory subsystem set as 2.3 gigahertz, the CPU frequency cannot go above 2.2 gigahertz. Effectively, this disables turbo boosting in the CPU. So on the left-hand side on the column, we have the CPU frequency governors. There's 4 main ones: the performance, which always pegs the highest performance; on demand, which pegs the CPU frequency based on demands; you have shared util and user space, which set the frequency manually to a frequency that you choose. So as you can see, when memturbo is on and the memory subsystem frequency at 2.3 gigahertz, the CPU frequency is at 2.2 gigahertz for the top 3 governors, and then it is set to what the user wants it to be. If you then look on the memturbo off columns, the memory subsystem frequency is no longer at 2.3 gigahertz, it is lower, but the CPU frequency is now higher. So for performance and on demand, the CPU can now boost to 2.5 gigahertz, but the memory subsystem now has to clock lower. And interestingly, when you set in user space, you set your CPU frequency to be 1 gigahertz, the memory subsystem is set at that same frequency. So if you set your user space governor to use 1.4 gigahertz, this is the frequency that's used for both the CPU and the memory subsystem. Now, what's the side effect of that for performance? So here is, again, stream. On the left, you have a plot for memturbo off, and on the right, you have a plot for memturbo on. Looking on the left first, here you see that performance on demand and shared util perform in the same way. So especially if you look at the triad performance, it's the same across the 3. But then you go to user space, and from 1 gigahertz onwards, and the performance is really low. And it increases gradually as you get to 2 gigahertz. But it is, even with 2 gigahertz, it is significantly lower than it is with the other 3 schedulers. Excuse me, governors. On the right-hand side, where you have memturbo on, the performance is pretty uniform across any of the CPU frequency governors. And this is because stream is a memory bandwidth benchmark. And here, with memturbo on, your memory subsystem sits at the highest frequency. And actually what becomes clear is that the CPU frequency is completely irrelevant, at least for performance. The blue line on these plots is power. So that is the amount of watts drawn per node. And as you can see, there is a significant dip, even when memory turbo is on, when you go to user space 1 gigahertz setup. So your performance of stream does not change, but your power draw drops by around 30 to 40 watts. So this is really significant. And the setup that we chose for our system is to have memturbo on at all times. We also set our nodes up to use the performance governor by default, which makes the power draw quite high. But it is possible as a user to turn this down if you know that your code is memory bandwidth limited, so you can reduce the frequency that is used for the CPU. A little aside on turbo boosting, and the reason we turned the memory turbo on and thereby disabling the CPU turbo boosting is that DVFS, or dynamic voltage frequency scaling, really reacts to the thermal state of the CPU. So if your CPU is very busy, it is very hot, and then DVFS will turn down the clock frequency. But if your CPU is quiet, and it is therefore much cooler, you get a higher clock frequency. Now, this is slightly counterintuitive, because if you have a code that really stresses the CPU, as in it's CPU bound, you'd want a high clock frequency, not a lower one. But the thermal state reaction means that it actually will be lower. So if you have a compute-bound application, you have a busy CPU, and if you have a memory-bound application, you have a quiet CPU. So the frequency scaling isn't necessarily doing what you'd need it to do for best performance. So unless your application really benefits from a higher clock frequency, the chances are that turbo boosting will not do anything other than waste energy. You're not going to get any better performance. So a couple of extra examples now on work that we've been doing with applications. So one of them is just looking at how the ARM compiler in particular has evolved over time. So this is an example of HPCG, which we've run up to 32 nodes. And comparing the ARM compiler and performance libraries version 19 with version 20. And the compiler options used in both cases are exactly the same. The version 19 run uses OpenMPI 4, and the version 20 run OpenMPI version 4.0.2. There's a slight difference here. But it's interesting to see that the ARM compiler is maturing nicely. So for HPCG, without changing any of the compiler options at all, we get a 6 to 7% improvement on the lower node counts and 2 to 3% improvement on the higher node counts. And here's an example of code called ImpCompact3D. It's a high order finite difference flow solver that had never been run on ARM before. And this was ported to ARM without any code changes at all. All that needed to be changed was some compiler flags to get the code to build. Once the code was built, it showed excellent performance, scalability out of the box. These lines here are for two different test case sizes, 513 cubed and 1025 cubed, running with the G-Fortran 9.2 compiler and the ARM Flang 20 compiler. And as you can see, it runs across the entire machine up to 4,000 cores, exhibiting perfect scalability and excellent performance. So just to sum up, since we received Fulham, since it was installed just under 2 years ago, we have done a lot on the system software side, in particular, new operating system, new network and communication libraries. We installed a new resource manager batch scheduler. We've also added Lustre storage, which I haven't really mentioned here. But as a result of a lot of work and a lot of bug fixing, we now have a very stable, very reliable, and easy to use system, as is evidenced by codes like ImpCompact3D, which just ran straight out of the box. And that way we are fulfilling the aim of the Catalyst program, which is working towards making the ARM ecosystem as mature as possible. Thank you.